Welcome, Earth scientists. We are here today to learn about plate tectonics and the famous guy who helped create this concept back in the early 1900s by the name of Alfred Wegener. I know it's spelled Wegener, but it's Wegener. He's a German scientist, actually a climatologist and geologist who died a martyr for his cause in Greenland, trying to prove and find the smoking gun that would prove his continental drift theory. So essentially, in 1915, Alfred Wegener wrote a book called The Origin of Continents and Oceans, highly controversial at its time because it hypothesized that all the continents used to be together somewhere around 250 million to 200 million years ago and then started splitting apart 200 million years ago and have been moving around ever since. So scientists around the world said, have you lost your marbles, basically? While it sounds like a good idea, you don't have any smoking gun proof. You have circumstantial evidence. And they wanted the smoking gun in order to prove that. So essentially, Wegener died not knowing that his concept would actually revolutionize all forms of science and has been proven definitively in the late 70s, early 80s that this is definitely the case, that his idea of continental drift occurs. The supercontinent that Wegener named was called Pangaea, and we're going to look at Pangaea right now. Pangaea represents a cluster of two different groups of continents. The northern one's called Laurasia, and the southern one's called Gondwana land. That's Gondwana for short. So I want to point out that India is stuck on the southern hemisphere right now. That's a big story in plate tectonics, because around 30 million years ago, it cut loose and ran towards the northern hemisphere, smashing into Eurasia as we know it today. So we'll be looking at that shortly. So when did this happen? During the Permian period, Pangaea was fully assembled by then. That's the tail end of the Paleozoic. And by middle to late Triassic, we begin to see evidence that plates were starting to split apart. By the Jurassic period, not only were they splitting, new ocean basins were opening, like you see right here. In the Cretaceous period, notice how far the Atlantic Ocean basin has spread in comparison to what it used to, and that there's definitive separation between Africa and South America, Antarctica, India, and Australia. And so you come here and you look at present 50 million years ago and compare it to present day, you're going to notice there's even been some changes, and here's India over here getting ready to do its smashy thing up here to Eurasia. So continental drift was an idea well before its time, and the evidence that Wegener used was, and some of it's more than just circumstantial, it's actually pretty good, solid evidence. But again, the scientific community rejected his theory as just being hypothetical because it didn't have a definitive, this is how it happens mechanism. We had proof that it happened, we just didn't have the smoking gun of what caused it to happen. So you might go, well, yeah, this is an obvious thing, Professor Wegener, that these things fit together like a puzzle. Well, not exactly. From a skeptic's point of view, we could have erosion along a coastline to where the coast of Africa and South America fit beautifully together, just randomly. Be kind of hard to do that, but nevertheless, you could skepticize that and say, okay, that's possible. Well, the truth is, Wegener didn't know he was right about this, but it's not along the edge of the continent that's exposed. It's along the edge of the continent that is the continental shelf. So when you follow the continental shelf down to where it meets the oceanic plate, that's the perfect fit. And that wasn't proven until the latter half of the 20th century. So one of his really big compelling pieces of evidence was fossils that are found on certain continents, especially in Gondwana land. This is a special type of freshwater reptile, and the freshwater reptiles don't have the ability or the genetics, or should I say even the bone structure, to travel several thousand miles between these two continents today. So Wegener theorized, okay, they must have been together at some point for them to be able to get into the same habitats. There's other fossil evidence that's more compelling, I think, than this particular reptile, and that's a plant fossil that's found in all of the southern Gondwanaland continents that existed, called Glossopterid. That plant is found at a very narrow window of latitude and would have required very specific temperature conditions and rainfall conditions to exist, indicating that the continents must have been close together at one time. Moving on to Wegener's next piece of information or data, which is actually very compelling, is where the continents were smashed together, like right along in this area right in here, we should have matching mountains. And if those mountains have eroded, we should have matching sediments on both sides, and we do. Today we can date the geochemistry and the isotopic data, meaning the age of it, to match equally, like the rocks in Europe and North America that completely match. So that's a very big piece of compelling proof. Another piece of really compelling proof that Wegener had was restricted to the southern continents of Gondwanaland, and that was evidence of glaciation following moraine deposits. Moraine deposits are rubble that's left behind, and there's a variety of different types, but the key we're focusing on here would outline the edge of all of these continents, and those are called moraine deposits. So if you look at where those same deposits are today, it'll kind of show you where the little blue arrows are here. That's pretty compelling proof that they shared a similar latitude in geologic past. So basically what we know about plate tectonics today, most of that came from World War II. You have to think back to Pearl Harbor days, back when we got a surprise attack on December 7th of that year, and we weren't ready for it. We were thinking it would hit Midway, which is an island halfway between Hawaii and the Aleutian Trench. But our ships are all clustered in at harbor, or at Pearl Harbor, and so we wouldn't be caught off guard again, and we could fight the war. And when it became obvious that we would need to map the bottom of the ocean floor. So essentially what happened was that we got busy mapping the ocean floor using sonar technology, where we would send sound waves down, bounce them off the bottom of the ocean floor, bounce them back. The return time would give you the elevation of the bottom of the ocean floor. To our surprise, we discovered several things: that the floor of the ocean was not completely flat, that there was a giant mountain range, that there was a variety of ages of different types of features on the bottom of the ocean floor called seamounts, and that the floor was moving. Yeah, you caught that last part right, that the seafloor was moving. That was a big question. So what we did after World War II was we start drilling holes for the deep sea program, and we'll get through with that. Essentially what we did was after World War II, we started drilling holes in the ocean floor to determine its composition, its age, and we were able to discover some very, very interesting facts that led us to prove Alfred Wegener's theory that continental drift is real. So we know that the Asthenosphere is the section right beneath where our plates are in the top of the mantle. This is where convection occurs. This stuff is hotter and weaker than what we call this material right here, known as the lithosphere. And the lithosphere encompasses two parts. It encompasses the upper part of the mantle, which is very rigid, and then oceanic and continental crust. So if I have movement in the mantle, kind of like a lava lamp, then that material will be moving, and it can release every so often areas of mantle hotspots. And we've got over 50 hotspots that are active today. That leads to the fact that there's a variety of different types of plate boundaries that are in existence today. Plate boundaries simply represent where two plates exist, and if they're pulling apart, if they're coming together, or they're moving sideways. So the type of plate boundary you have also dictates the type of geologic phenomena that you might have, including things like earthquakes, volcanoes, tsunamis, things of that nature. So we're going to start with the absolute most important of the bunch, which is called divergent plate boundaries. The prefix di means to pull apart. So diverge means you're going apart, away from each other. So you think about a divergent plate boundary, it's two plates that are separating, and the big question is why. They separate, let's say on the ocean floor, for example, because we get an area of crust that develops an ocean ridge. Well, the ocean ridge looks like this, and the reason it happens is you've got a hot spot that's pushing up on the crust, and when it does, it splits it apart, and you get a ridge, mid-oceanic ridge, MOR. So that actually causes the seafloor to spread apart, and lava comes up to the top of it and solidifies on the surface of the ocean floor. As it hardens and new lava comes out, it continues to pull the mirror image away from the middle of the mid-oceanic ridge. So technically I should see the same lava on either side of the ridge, and it's getting further and further apart with age as more lava comes out. So this looks exactly as what I was just describing, except this is showing you divergent boundaries can also be on continents. A Rift Valley is actually a continent, but we're going to look at this for a second. Let's just say for sakes that this is in the middle of the Atlantic Ridge, and you've got this area of crust pulling apart, and you can see this is highland right here, because that's where the crust went like this, where the magma came up and spread the crust apart, separated it and pushed it back, causing us to have a valley between them. So I should be able to follow the lava on this side and the lava on this side until it finally collides with something else. We call it the collision point, a subduction zone. There are two types of divergent plate boundaries. Most of them are along mid-oceanic ridges, like you would see the mid-Atlantic ridge right here. They're out in the middle of the ocean basin. The key is that we can also get them on continents. Let me show you one of the most famous ones in the world, which is called the East African Rift. And this is stage one, where the east side of Africa is separating because you get a hot spot that's causing the crust to weaken. And as it weakens, it separates and moves on either side. It's moving apart. And you can see the arrows here and here indicate the crust is pulling apart. Given enough millions of years at, let's say, a couple of inches to 5 or 6 inches a year, let's say you put that over 20 million years, this could be a water body known as a sea. And the definition of a sea is different from an ocean because it's restricted somewhere. A sea usually doesn't have a straight through process. If it does, it graduates up to ocean status. Once I separate that linear sea, which is the Red Sea, and there is a small little part of the Red Sea plate, or this area that's part of the African and Arabian plate, here's the Red Sea, and you get this little plate up here that needs to separate, almost like a wishbone. When the wishbone is completely gone, we're going to end up with this situation right here where we have graduated to an MOR status. Again, that stands for Mid-Oceanic Ridge. That's a test-related question. All right, so as the ocean plates diverge apart, eventually they collide with the continent. When they do, we can create something called a subduction zone. Since oceanic material or plates are made up of a little bit more metals, they're more dense than continental plates. You have to imagine they're real thin, but really dense, like an armored car. And continental plates are real thick, like styrofoam, made up of lighter weight material, but extremely durable. So what will happen is the ocean plate, when it collides, will actually dive under the continental plate and create subduction. Well, as that subducting plate goes under, some of it actually attaches to the continent. We call that accretion. We'll get to that in a minute, where you glue on a permanent new piece of land to the continent, and the rest is torn down and partially melted and fuels up volcanoes along subduction zones, or makes what we call continental volcanic arcs. The best one I could give you would be right here in North America, and that's the Cascadia Range, aka Mount St. Helens. So here's that classic look. Here's a subducting oceanic plate. Notice as it comes down deep enough, we get melting. So you might go, well, how far down is that? usually beyond about 55 kilometers, 50 or 55 kilometers. So in this area from here to here, since we had the rock cycle last time, this is where I'm going to form metamorphic rock right in here. Eventually that rock's going to get too deep and it's going to melt and it'll turn it back into igneous, fueling hotspots to rise to the surface to turn these things on via volcanoes. So for testing purposes, there's two things associated with the subduction zone all across the world. On the ocean side of a subduction zone, you have what's called a deep sea trench. This was a discovery we made during World War II that surprised us that these things actually happened. And the reason they do is this ocean plate makes a nosedive and it leaves a great big crevice where this action happens right here. So the ocean side of a subduction zone has a trench, and the continental side always has mountains and or volcanoes, usually both, that occur. Sometimes you can get two ocean plates that converge together. Usually one's slightly denser than the other, and they form volcanoes out in the middle of the ocean for no reason whatsoever. So the Aleutian Trench is an area like that. The Marianas Trench is an area like that. The Tonga Islands are an area like that. So oceanic to oceanic convergence does happen. It's not as common as oceanic to continental subduction, but nevertheless they make the same evidence of proof of a string of volcanoes. So if you get an oceanic to oceanic crust type situation, you'll get one set of oceanic crust that's slightly denser, and it has to do with the minerals that make it up. And then you'll end up with an island arc out in the middle of the ocean basin that just doesn't make sense why it's there. Sometimes we get two continents that smash together. Really weird stuff happens when this occurs because they're similar in density, so instead of sinking, they rise. And this is where you get the largest or tallest elevation mountains in the world. Don't confuse that with total relief. It's total elevation. So when this occurs, we end up with a Himalaya or Mount Everest type situation. So here's an example. I've got continental material and continental plate over here, and they're smashing together. So it'd be like two cars hitting head on. They smash and everything uplifts. When they do, notice all this rock deformation that happens because these sets of rocks are going to get thrusted upwards and they're going to get folded, faulted, cracked, and makes a humongous mess. So if you're near one of these and you live near one of those, you should expect that you could get some pretty serious earthquakes from time to time. Hopefully not a volcano. If you did, it would be the worst type ever because you'd be cooking through a huge volume of continental crust, which is high in silica. So the reason that subduction volcanoes are pretty dangerous is they melt continental and oceanic and they blend. And continental material is high in silica, so if you get a subduction zone volcano that mixes more with continental minerals, then you're going to have a higher percentage of silica, which makes them more dangerous. So the Himalayas formed this way. They started tearing off during the late Cretaceous period in Gondwana, and by about 30 million years ago, it made its connection point right up here. And here's the 30 million year marker right here. And by 10 million years in present day, it connected right in this section right here. And it's still uplifting today. And you might wonder, how do we know that Mount Everest is still uplifting and the Himalayas are still uplifting? It's a brilliant question if you thought it. Here's how we know. We can put GPS stations on these mountains now and determine their elevation using satellite technology and pinpoint their movement, and we can see, in spite of gravity and erosion, that the mountain is uplifting by approximately 1 inch per year. So, in other words, India is still smashing today. That plate tectonic story is still in action. So this is a very, very young mountain range, and that's one of the reasons it's the tallest, and it is definitely one that we could say happened in similar places around the world back when Pangaea was intact. So the collision of India and Asia produced what we call the Himalayas today. So you've got India coming in 30, 25, 10 million years ago, making its collection point right here where it connects. And then, since they're approximately the same density, uplift happens. So these just would have been volcanoes, but not exceptionally tall structures. But when this collides with this, different ball game. Here's the way it looks today. So you can imagine how important, just thinking ahead towards a little later in the semester, if I have glaciers up here and their meltwater services India, do you see how important that would be for their drinking water supplies? And let's think about in your brain how important it would be if climate change produced such a way that you couldn't have the same volume of glaciers up here, and that would significantly limit the water that runs to India. That is a true problem that they face today. Consider they're the second most populated country in the world. It's food for thought, really water for thought. Oops, wrong way. All right, let's move to the third type of plate boundary called a transform plate boundary. This is when one plate slides next to each other, side by side. So you don't have any collision, you don't have any pulling apart, there's just friction, for a better lack of words. So we don't get crust made and we don't destroy it here, but we do lock it up every so often where rocks are held like this and they're pushing and pulling and one day they slip. When they do, they can slip catastrophically or in a very minor way. And the place I can think of you would recognize the most frequently would be the San Andreas Fault. And it doesn't just run through California, but the consideration of where California is. Think about the areas that have earthquakes. And most of them are pretty small in California, but occasionally we get a fairly large one. That's that hang-up moment I was telling you where the rocks have been building up stress and one day they just slip and slide. Two fairly significant ruptures have happened in the last 100 years, and we know by watching the stress buildup of the movement of plate that we're due for another one before long. So transform boundaries may not be glamorous in terms of having volcanoes and big mountains and stuff like that, but they're extremely important to property and human life because they can redecorate a yard or a fence even over a few years as stress builds up and the plate moves. If it's, let's just say the Pacific plate is moving at about 5 centimeters a year, and the North American plate's moving about that fast the other direction, you could see that we could end up moving cities and moving land over a short period of time. Another place you'll see lots of transform boundaries is where we have divergent plate boundaries at the bottom of the ocean. And it makes long lateral faults like these that you see right here, and that happens from where the diverging crust is pushed backwards on either side and it fractures and creates faults in these rocks right here. So we have lots of little bitty earthquakes at the bottom of the ocean floor. So we mentioned the San Andreas just a minute ago. It's active, but I want to point out that it's active along this boundary here, starting about right here, all the way through California and then out into the ocean. So just to say it's in California is an untrue statement. By the way, the San Andreas is not going to cause California to fall off into the ocean if we have a rupture. Not like the movie that you saw in Hollywood. That's just not going to happen. So what you need to know is that this is oceanic crust right here, so it should tear off and continue moving with the Pacific plate as a large island. Here, however, is a different ballgame. If you look at these kind of reddish pink areas, these are mid-oceanic ridges where the Pacific plate is separating from Juan de Fuca. Juan de Fuca is subducting under North America right in this area in the Cascadia Subduction Zone, and it creates famous volcanoes like Mount Shasta, Mount Hood, Mount Rainier, Mount Adams, some very famous places that I went to on sabbatical, and I can tell you that they're incredibly active today. So how do we find the smoking gun for plate tectonics? First of all, the smoking gun boils down to something we discovered in World War II. Think back to what I said about Pearl Harbor. Think about what happened in Pearl Harbor. What a bummer. We get those small little submarines that came in and we were not able to detect them. So the military said, well, we better figure out where those enemies are hiding those submarines and we need to find where we can hide ours. So let's get busy testing the bottom of the ocean floor and mapping it out. one of the testing tools they did was they were looking for iron signatures where that should be a submarine, right? That could be hiding at the bottom of the ocean floor. To their surprise, when they flew over with the instrumentation that finds magnetic things like iron metals, they found the entire ocean floor was pretty much covered with this stuff. So there couldn't be submarines all over the ocean floor, and that led them to a big giant hypothesis of, well, the ocean floor must be made of stuff we didn't realize it was. When we got down there after the deep sea drilling program and were able to, or after World War II, excuse me, and started doing the deep sea drilling program, we were able to prove this beyond a shadow of a doubt that beneath the muds that have accumulated over time, a couple of miles of mud were present, and then poof, or not even a couple of miles, really a couple of thousand feet of mud was there. And then we had oceanic crust made out of lava, basalt to be exact, very mafic. So then we started age dating the floor, and that was the big shocker, because not only did the age of the ocean floor progressively get older away from mid-oceanic ridges, there was a mirror image of age on either side of the MOR until you hit a subduction zone. That is the smoking gun of plate tectonics. We call those magnetic stripes. So I'm going to show you not only can we capture the magnetic field of the Earth back in the time that these layers were laid down as igneous magma and lava, we can also age date them. Not just the polarity, but we can actually physically age date them. So you have to imagine that all the magnetic minerals that are in this lava, when they're molten, align themselves just like a compass with magnetic north. So we can determine if magnetic north was like it is today or if it's reversed and pointing the opposite direction. But then we can go in and age date these things. That's powerful information. Lava flows in particular are pretty good about providing good usable radiometric dating. That's not carbon dating, that's radioactive isotope dating. So paleomagnetic reversals look like this. We have a period of normal magnetism, we'll make it this color. And here's your MOR, your mid-oceanic ridge, and lava spills out on either side. So as it pulls apart, new lava comes in, the place where the old yellows were, and it pushes the yellows back, mirror image on either side. And mind you, the yellows are headed to continents on either side. At the next stage, I have, again, a normal polarity. The pinks were reversed. And notice my original yellows are way over here. So they too, this one and this one should date the same. This one and this one should date the same. So this one and this one is this stripe and that stripe. This one and this one is this stripe, and that is this stripe right here. So we've been able to age date the entire ocean floor. This is remarkable. This is what Wegener did not have in his ability back in 1915, nor did he have it when he died about 15 or so years later. So this was extremely valuable information as a consequence of doing World War II. So what we know is that we can see there's a pattern of polar wandering, meaning reversals throughout geologic past. We can document that on the ocean floor, and we can also see that there's a trend and a pattern, but not necessarily with speed. You might think that the speed of plates should always be the same, and it's not the case. It's actually very different, and we can look at the width of a magnetic stripe to determine the thicker the width, the faster the movement of that seafloor spreading was at that time. Another thing that tested the plate tectonics model that Wegener had was looking at earthquake patterns. Now this was well after his death that we were able to prove this, but we were able to look at the bending of a plate and determine at what angle the plate was subducting simply by following shallow, intermediate, and deep earthquakes. So looking at the focus is where the earthquake occurs inside the Earth. If you're thinking of where it happens at the surface, there's a different name for that called epicenter. So once we started measuring this particular patterns and seeing that there was definitely a rhyme and a reason to how this worked, we were able to map the angle of subduction. That helped us know where the areas of vulnerability are most in the world currently today for risk for significant, huge earthquakes. We could also trace why certain plates disappeared and why we have mountains further interior in places like the Rocky Mountain Range today, simply by looking at the angle of plate subduction. This was a big deal when we found this out. So here's a earthquake map, kind of showing where the earthquakes are around the world, and the heaviest line is right around the Ring of Fire. In all fairness, we should call this area the Ring of Shaking as well as the Ring of Fire. And I want you to look at the red and notice that there's a definitive line where the red earthquakes are, and those represent the deepest earthquakes. So what's deep? Usually greater than 150 or so kilometers beneath the Earth's surface. Intermediates are up to about 50 or so kilometers, from 50 to 150-ish, and then shallow ones are less than that. So shallow ones should be the most common, the blue line, and the more shallow an earthquake is at a subduction zone, the closer to the surface it is, the more dangerous the earthquake can be if it releases a tremendous amount of energy. So bottom line is, if we're able to look at all three, shallow, intermediate, and deep earthquakes, we can follow the path and the angle of a subducting plate around the world. So this is what it looks like. This is called Benioff, and Benioff is just simply named, if you look at that name right there, Benioff is the main guy that discovered this pattern of earthquakes. And notice that we can actually trace the movement of a plate simply by looking at the depth of focus or foci of earthquakes around the world. So we know, for example, what's happening around Japan, and we can see where the most dangerous places are going to be by looking at the frequency, the depth of the focus of each earthquake, and plotting those into a chart like this to actually see a story. So this is really designed to help protect human health and the environment by knowing the areas around the globe that are subject to some serious earthquake problems. All right, so another way we tested the plate tectonics story or model was by ocean drilling. I referenced this several times. The initial deep sea drilling program was called the Glomar Challenger. It's now actually called the GEOL Resolution, and it's still working today. But the oldest sediments that we found on the ocean floor dated back to approximately, test question, 180 million years old. Think about that, 180 million years old. That's not very old, considering the continents are up to about 3.8 billion, that's with a B instead of an M, years old. So ocean basins are very young, and that posed some questions is, how is that possible? And that's when we found the magnetic striping, and we were able to prove that the seafloor is constantly moving, and once it hits a subduction zone, it's recycled. That was very, very new information after World War II. So here's the Glomar Challenger now, the GEOL Resolution today, and we're still testing that theory. We've been working on drilling holes around the world, and what we found was a storyboard that the ocean floor was not what we expected it to be. It has mountains, it has trenches, it's constantly in a state of change, it's not static. It's made of different stuff than we thought it was made of. The crust is very mafic instead of lots of sedimentary rock. Just a lot of surprises all the way around the process of testing the bottom of the ocean floor. So another way that we can test the plate tectonics model is through understanding hotspots. And this was discovered by a guy by the name of J. Tuzo Wilson. So we had Alfred Wegener doing Continental Drift. For this class, we'll focus on the hotspot guy, which is J. Tuzo Wilson. And he actually figured out that there are areas of volcanism around the world, and he hypothesized that this must come from hotspots that are resting under that crust, whether it be under an ocean floor or on a continent. Well, the obvious place that can show this in the world is the Hawaiian island chain. And you're actually looking from the top of Mauna Kea on the big island of Hawaii. I took this shot. And you can see multiple little volcanoes that formed on top of a big giant shield volcano. And Hawaii is just a series, the actual island of Hawaii that is, of 5 volcanoes. And so every one of the islands you see was made exactly the same way. In other words, they passed over the hotspot at some point in geologic past and created an island. So here's some evidence that shows us how this works. We can see plate tectonics happening before our eyes. And this is what happens. Right now we have a very active volcano in Hawaii called Kilauea. And there's a big caldera, which is where a volcano is collapsed inside of itself. And here's about 30 or 50 miles beneath the surface is the actual Hawaiian hotspot. So it's going to send out magma chambers. Here's what we got, what's called a sill, and then it works its way up as a pipe and an exit point at the Pu'u'u'o'o vent. And Pu'u'u'o'o will erupt, and when it does, it produces lava flows that can make it to the ocean floor, or to the ocean surface actually. First of all, the distance from here to here is multiple miles. In some places more than 10 or 15 miles. Some places it's as close as 3, depending on where you are with proximity to the ocean. This whole section here is matter of fact, this entire area is a national monument. Just so you know that. It's a very neat place to visit if you're on the island of Hawaii. So what will happen is we can follow these lava flows and see them super cool when they hit the Pacific Ocean via lava tubes. And I'm going to show you what a lava tube looks like in just a second. And then that super cooling at this point right here where you see the big cloud of plume, that creates volcanic glass, which then gets beaten up by waves and turns into black sand beaches. So here's what a lava flow looks like, but underneath some of these lava flows there's going to be some areas that are very red, and this is starting to make one here. Do you see the cap on top? Once a cap gets forming, the lava stays insulated and it continues to flow down towards the ocean. If you're lucky enough, this is what the cap will look like after it's hardened. It really insulates it like a coffee cup and keeps it from cooling down and stopping the flow of that lava. So that's really important. That's the function of a lava tube, is to keep that lava insulated. Ultimately, this is what happens. You get a hydrovolcanic eruption. So just to kind of put your reference, so here are some of the lava tubes. You can almost see them right in this area, right in here. And I was in a helicopter flying over this part of Hawaii, following the lava that you just saw in the prior picture here, all the way to the ocean, and watch that lava fall into the Pacific Ocean, creating that hydrovolcanic eruption. The key is it doesn't make black lava once it hits the ocean. It makes this stuff right here. This is volcanic glass. So really, black sand beaches of Hawaii and anywhere in the world that makes it just like it is volcanic glass. It's not just black lava, known as basalt. So the Hawaiian Islands have not been stationary, and we know this for at least 82 million years. And how do I know that? There is a seamount that's well underwater right at the point where I have my cursor right here, called Mihai. And Mihai dates back to pillow basalts there at the very bottom of the ocean. And pillow basalts are globs of material that glob out and sink and kind of solidify against the side of a volcano. And we can date those back to 82 million years. So you come down to this point, this is about 45 to 55 million years ago. This is midway. And then the modern island of Hawaii sits right here. And that's less than 1 million years old. So I want you to reference that there was a bend in the path of all of the plate drifting. And we think that has to do with India smashing in about the same time, 45-ish, 55 million years ago, beginning its change in course, which kind of knocked several other plates off kilter. So what I'm telling you is that this particular, all these seamounts that are underwater here, and every island that's exposed along this section, all started off at X marks the spot where my cursor is today, where Hawaii is. You begin to realize that this is multiple thousands of miles of kilometers of island arc. So the Hawaiian Emperor Seamount is this gigantic piece of evidence that we have of continental drift. So how do we measure plate motion, and how do we know that plates are really moving? Because we have the technology to know that today. So I'm going to show you because it's really kind of interesting. We use special space technology to do it. GPS is one, but we use VLBI in order to establish baseline movement of plates by using space technology with satellites. And so these combinations of technologies put together allow us to understand and be able to utilize that information to paint pictures of where plates are moving. In particular, this is what I'm talking about. Notice the arrows all represent centimeters per year. This kind of shows you how fast certain plates are moving and where they're moving in what direction. So this particular plate right here in yellow is moving at 5.5 to 7 centimeters a year. If you come a little bit further north, it's moving in a little different direction. So you're like, and you can follow the Pacific plate. Notice that it's kind of moving in different directions at different speeds. Notice the Pacific plate is moving much faster than any other plate in the world. And that's important because that's where most of the activity of the Ring of Fire is. Also where the worst earthquakes, the worst volcanoes are. Second worst would be this area right in here. You're very familiar with that from Sumatra. Shouldn't be a surprise that it's second in line for moving very fast. So interesting stuff to think about is that we're measuring plates. Today we know they move. Let's just have a recap. Wegener knew there was continental drift and had a lot of superficial evidence like the fit of continents, fossils on all different continents from Gondwanaland, glacial deposits on Gondwanaland. He had knowledge of the fact that he was certain that they were all together to make a supercontinent called Pangaea. And it wouldn't be till World War II that set the motion or the key actions in motion for us to discover magnetic striping, seafloor spreading, and ultimately be able to discover that the ocean floor is made up of completely different composition, a very young age, as compared to the continents, and it's regularly being recycled via subduction. So more to come from Earth science.